21.
I had a question. When you said that when the value is closer to 1, it would favor the reactant?
No, both.
Both?
When I say close to 1, it's anywhere close to 1. It could be like 10, 20, but in this one it's like 9,000. 9,000 is going to favor what? The reactant or the product? Product. And so I'm not sure if we talked about this. Did I talk about this, pH 7? And I asked, is that the equilibrium pH or is that the initial pH? In other words, they give us the H plus concentration. And when we fill out the ice table, do we put that in the initial row or do we put this at the equilibrium row? And so we read and compute the equilibrium concentration. So we want the equilibrium concentration of iron 3+, which is here. And so we're looking for that at pH 7. pH 7, I talked about power functions, right? Or did I? Yeah. And so this is pH 7 just means it's 1.0 times 10 to the minus 7 molar as far as the concentration of the H plus goes. And so all we need to know is that the initial H plus or is that the final H plus here? It's the final because they're saying at. So it's equilibrium iron at that pH. Therefore, this has got to be the final. And so this is a pretty straightforward problem. Did I set it up already? No? Okay. So we'll set it up right now. So our K expression is going to be the activities. We'll just do KEQ here. Oh. No, I got cut off. So anyway, our K is going to be the products of this, which will be iron 3+ to the first, and then water. What's the it's 1 and it's cubed, 1 cubed. And then this is going to be iron 3 hydroxide solid. The activity is what? 1 times the hydroxide ion concentration cubed. All right, the 1's cancel. And we're left with this. Or is that, I'm sorry, it's not hydroxide, it's H+. Let's take a look here. Yeah, H+ through cubed. So I need to correct that here. So we know what the K value is that's given in the problem. The K value is 9.1 times 10 to the third. We know what the H+ concentration is. The H+ concentration is 1.0 times 10 to the minus 7. And so the only unknown is the Fe3+. So we just solve for this. So we don't even have to set up an ice table. I mean, we have enough information to solve it. But most problems we will set up an ice table to figure it out. Okay, so that's 21. So 57.5, when I see a K like this, I say, it favors kind of both. We expect significant quantities of both reactant and product. However, just a slight, favoring of the product. So like 50 to 1. But it's not like 1,000 to 1. All right, equilibrium relationships here. And so these are just equilibrium style calculations. And so all these types of calculations, we're going to set up an ICE table. Sometimes they give us KC, sometimes KP. So we might have to switch it. Direction of chemical change. The direction of chemical change, we usually calculate Q, unless we can see it. I mean, for example, if we have 0, from 0, the only way we can go is up. And so we can predict that it's got to increase. But sometimes it's difficult, and if it's difficult, we calculate Q and compare it to K. Did I talk about that already? Calculating Q? All right, let's talk about that here. Direction, we usually go to the side with zeros. And so go to the side with zeros, like 0 concentration, 0 pressure. Zeros. If there's no zeros, I mean, if it's difficult to figure out, let's say there are no zeros, then what we do is we calculate Q, or calculate Q. Q is called the reaction quotient. And it's equal to the initial concentrations of the product over the initial concentrations of the reactants. And then what we do is we compare Q with K. If we calculate Q with the initial concentrations and we get the proper ratio, which is K, then it's at equilibrium. And so there's no change. If Q, I. If Q is less than K, then we don't have enough product. And so the change goes in the left to right direction. So in other words, we have minus X plus X kind of thing, and X. You know. If Q is greater than K, we have too much product. And so the change is going to be plus, minus. And so in other words, this would be forward change, this would be reverse change here. So we'll say forward reaction, reverse reaction here. Okay, and then the other thing that let me just save this here. Is extent of change. Extent of change, there's a little weird symbol that they do for extent of change sometimes. It looks like this. But what we're going to do is we're just going to do our ICE calculations to figure it out. And so, we set up an ICE table.
For the equation for Q, is on the top is the reactant, the H, reactant. Is there supposed to be a superscript?
Yeah, thanks. There should be a little superscript H here. So this is just like the K expression, except that we use the initial concentrations rather than equilibrium concentrations with this. All right, so these are just ICE calculations here. You can take a look at it. So we set up an ice table. Sometimes it's hard to determine which direction the change is. Sometimes it's easy. You know, it goes to the side with zeros. That's when it's easy. But when they're all non-zeros, then we don't know. Like, for example, this reaction here. You know, we have chromium, but we don't have any of these. So it's got to go to these, you know, side with zeros. And so ice. These are ice calculations using pressures instead, kp. This is the same thing, except rather than using molar concentrations, we use pressures, either in atmosphere or bar. Then we have Le Chatelier's principle. These are all qualitative. There are some quantitative Le Chatelier's principle problems. And then we have these reactions with very small or very large K values. And when we're dealing with very small or very large K values, then there are certain tricks to make the math easier. We could try to use these tricks for all ice calculations, but they don't work as well when K values are close to 1 or are just moderately big or moderately small. And so when we look at this one, look at this K value is 10 to the minus 16. If you have a K value of 10 to the minus 16, that means it's heavily favored towards the reactants or towards the product? Towards the reactants, a very small ratio, so it's going to be heavily favored towards the reactants. When it's heavily favored towards reactants, then we think about a couple of things. One of the things we think about is how big is the change? Now, first we've got to figure out what direction the change is going to go, and then how big is that change relative. And then if we think about that, then we have to worry about how many digits our calculator carries. Do you know how many digits your calculator carries? 12? That's pretty good. My calculator only carries 10 digits. Why do you care? Do you know how many digits Excel carries in a calculation? 100. That's a lot. So Excel is pretty good. Why do I care? I care because I have to worry about rounding error. Let's say my calculator carries 10 digits and I have 12 digits. If I have 12 digits, am I going to be able to input 12 digits into the register? No, I'm not. So what's going to happen? Do you know what's going to happen? It's going to round it to 10. You can't carry 12 digits in a calculation. Sometimes the rounding is not a big deal, but sometimes it is a big deal. It becomes a big deal in scenarios where we have very large or very small k's, and so we have to really worry about it here. So we'll take a look at an example. We're going to look at number 74 here. Number 74, the equilibrium constant for the following reaction has been estimated to be 10 to the 20th at 25 degrees C. 10 to the 20th heavily favors what? Product. Estimate the equilibrium concentration of NH2 minus. What's NH2 minus called? Amide or amide. Give me one chemical property of amide. It's a base, yeah. And be a little bit more specific. Strong or weak? Yeah, it's one of the strong bases. We could give other properties of amide, you know, metathesis, what ions, what cations does amide like? And the last chemical property we'd look for is what? Redox. And we have to look at these things separately because, for example, I'll just do this as a quick aside here. Maybe I'll skip this. If we're looking at redox, it turns out that ammonia, and amide are roughly equivalent in terms of redox properties. All three species are good, what? Reducers. Because all three species are electron rich. Do you see that? How do I see that? I see that because all three species have nitrogen in the -3 oxidation state. And so I'd expect to be able to burn all three of these. If I burn all three of these are going to produce NOx. You know. However, when I look at acid-base properties, are all three species similar in terms of acid-base properties? No, they're totally different in terms of acid-base. Are all three species similar in terms of metathesis? No, totally different. But in terms of redox, then I treat them all the same, basically. And so we look at each, so we don't compare acid-base and redox at the same time. We just look at redox. Therefore, we don't compare like oxidation state and formal charge at the same time. The formal charge is really important here for acid-base properties. I mean, this is an acid, this is a base, this is a strong base. But for redox, it doesn't make any difference because that formal charge doesn't change the oxidation state of nitrogen. But we know that amide is a strong base. Estimate the equilibrium concentration of amide in a solution prepared by dissolving 0.0125 moles sodium amide in water. Sodium amide should be soluble or insoluble? Soluble. All sodium salts are soluble except for there's just a very, very small number of sodium salts that are insoluble. One sodium salt that's insoluble that we used to use a long time ago is sodium uranyl sulfate or something, or phosphate, uranyl phosphate, I think it was. Which contained the uranium cation, UO2+. We used to have a uranium cation in the lab here. I don't know what they did with it. They probably discarded it as radioactive waste. But it was depleted uranium. You heard of that, depleted uranium? Yeah. It's not so radioactive. It's lost a lot of its radioactivity, kind of thing. Why? Uranium is quite dense, way denser than lead. So, anyway, getting back to this. Is the result physically meaningful? So here's the reaction. We know that strong bases do what in water? Strong bases, do they ionize in water? They hydrolyze in water. Hydrolysis means they're going to react with water, break it apart. And so here, strong bases react or hydrolyze with water completely. So if I have an amide, I expect it to react with water completely to form hydroxide. And in Chem 1A, this would be going from a stronger base to a weaker base. So amide is a stronger base than hydroxide. And water is a stronger acid than ammonia. And so we're going from stronger base, stronger acid, to weaker acid, weaker base. And so we have driving force. We have driving force, we just say the reaction goes to completion. But what we're going to do in Chem 1B is we're going to see, well, is it really complete? We say that strong bases hydrolyze water completely, but does it really? So if we know the K value for this, which is estimated at 10 to the 20th, we can figure it out. Does it hydrolyze completely? And so let's set up the calculation here. So this is number 74, I think? Yeah. 4. And so the reaction is between amide and water. And this produces ammonia and hydroxide. Strong bases produce lots of hydroxide in water. Weak bases only partially hydrolyze water, so they don't produce as much. The more hydroxide we have in water, the more basic it is. the higher the pH is. So strong bases really increase the pH. Strong bases have pHs of like 9, 10, 11, whereas weak bases would have pHs closer to 7, like 8 or 9, you know. Depending on the concentration, you know. All right, so we have 0.0125. So what we do is we set up an ice table like this, and when I have a K value, the K value is 10 to the 20th or about 10 to the 20th, say about 10 to the 20th. And we're going to start off at 0.0125 molar here. What's the, you know what the molarity of water? The molarity of water is 55.5 molar for pure water. But its molarity doesn't change much. In other words, we say the activity of water, pure water, does it change much? No, the activity of pure water is close to, or is 1. So we ignore this. The activity is not going to change. So even if we consume a little bit of the water, let's say you start off with a gallon and you have, let's say, 9/10 of a gallon. Is it still pure? Yeah. And so pure liquids are like that. Ammonia is going to be 0 molar. And hydroxide is going to be 0 molar. And so normally, in order to figure out the direction of the change, we calculate Q. But do I really need to do a Q calculation for this? No, because I know the direction of change. The direction of change is I can go up or down from 0.0125. But can I go up or down from 0? No, the only way I can go is up. I cannot go down because if you have nothing, then you have nothing to lose. And therefore, you can't lose anything. And so what we're going to do is we're going to go down here. So this is 1. So this is going to be minus X molar. And water we ignore. And then ammonia is going to be plus X molar. And hydroxide is going to be plus X molar. Now, one of the things that we do, you know, in order to use some of these tricks that might simplify the math, I look at how big the change is. And we know that this is going to be kind of heavily product favored. And so how big do you think the change is going to be? I mean, 10 to the 20th. 10 to the 20th is what? How many is that? Like a billion? A billion is what? 10 to the 12th? Or no, 10 to the, billion's 10 to the 9th, sorry. A trillion is 10 to the 12th. What's 10 to the 15th? Trillion's 10 to the 12th. 10 to the 15th is quadrillion? I don't know really. I stop at a trillion. And so if I stop at a trillion, that's 10 to the 12th, and then I have 10 to the 8th left over. 10 to the 8th, I'm going to do, what I'm going to do 10 to the 8th, I'm going to take 10 to the 6th and 10 squared. 10 to the 6th is a million, 10 squared is 100. So we're going to go 100 million trillion. And so this is 100 million trillion to 1. You know, this is just crude estimate. But I expect it to be heavily favored towards the product. So I expect the change to be big. This is going to be a big change. So this is one of the things I look for in a problem. This is going to be a big change. I don't like big changes because, number one, we run the risk of round-off error, you know. Small changes are easier to deal with. And number two, we can't use some other tricks for simplifying the math. But I'm not going to use any of these tricks. We're just going to go ahead and calculate it. And so at equilibrium, I'm going to expect 0.0125 minus X, whatever X comes out to, molar left over. And then I expect to form X molar ammonia and X molar hydroxide. Okay, so now I'm just going to solve for X. So we have 10 to the 20th is equal to the ammonia concentration to the first power. And so, you know, this is ammonia concentration times the hydroxide concentration, both raised to the first power, divided by the amide concentration. And water is 1, so I'm not even going to include it. Everything's to the first power because all the coefficients are 1. And so 10 to the 20th is going to equal x times x. I'll just call it x squared, divided by 0.0125 minus x. All right, this seems reasonable. This is just a quadratic. And so I'm going to get this into quadratic form. So I'm going to multiply both sides by 0.0125 minus x. And so if I do that, then I'm going to get, on the left side, I'm going to get 0.0125 times 10 to the 20th minus 10 to the 20th x is equal to x squared. And then I'm going to rearrange this into quadratic form. X squared plus 10 to the 20th x. And then I'm going to change this to 1.25. So this is going to be minus 1.25 times 10 to the... So if I make the coefficient bigger, I got to make the exponential term smaller. So I'm going to make this 2 smaller and go to 10 to the 18th is equal to 0. And then I'm going to grab my handy calculator. I have a calculator that solves quadratics. But if this is homework or something like that, then you could just use a quadratic solver online. So I'm just going to go to quadratic solver online. So there's a whole bunch of these. Let's see if it works this time.
What calculator did you say you have?
I have the Casio. I'll show you. Casio, I have the FX, but it doesn't really matter because all the calculators have similar features. I have the ES Plus. ES Plus. I paid around, last time I purchased this calculator, I paid around $17. I got it at Target. I have the 5% discount at Target because I have a red card. So I did that. It's $17.39 at Target. But it's only $15.99 at Amazon. Wow. This is my calculator here. So this has a equation solver. It's the equation solver. Where is it? You have to go in the menu, the mode. This equation solver can solve up to cubic equations, which is pretty handy to have. And so it's essentially like this. I don't know about this. So all I do is I enter A, B, and C. So A is 1. B is 1 times 10 to the 20th. C is minus 1.25 times 10 to the 18, correct? And then I'm going to calculate, solve for x. And I don't know what's wrong with this. Something is wrong with this. Because I get x is equal to 0. Can x equal 0? That's no change. We expected, what did we expect? We expected a big change, right? And the other x value I got is x equals minus 1 times 10 to the positive 20. That's a huge change. But did I start off with 100 million trillion molar amide solution? No, that's impossible. So these numbers are impossible. So I don't know what is wrong with this. But this looks like my quadratic right here. Or maybe I didn't scroll down far enough. Let me scroll down farther. No, it's still the same. That's weird. And so I'd look and see, did I mess this up?
Is it the b squared of the b go away? We multiply
No, the b's still there because it's here. I'm multiplying both sides by 0.0125 minus x. So I'm going to get 0.0125 times 10 to the 20th right here. And then minus x times 10 to the 20th is going to give me minus 10 to the 20th x equals x squared. And then what I'm going to do is I'm going to subtract or add. I'm going to add 10 to the 20th x to both sides and subtract this 1.25 times 10 to the 18th, and I get this is equal to 0. Uh-huh.
I got 1/800 in my calculator.
Okay, change it from fraction to decimal form.
Okay.
And so just, there should be like an S to D key.
Yeah, it's 0.0015.
Okay. What calculator are you using?
I have TI-36X.
Okay, TI-36X does it too. So X is 0.0125. What's the other X value you got?
It was -1 times 10 to the 21st. I did.
Okay. Something's wrong with that online quadratic solver. So I was going to search through. That's the second one I tried. I'm going to search through some others. But there's definitely something wrong with that. But this looks correct. And so the two x values, 0.0125 and negative. We can't have a negative x because is it possible to make a negative molarity? No, it's impossible because you have to weigh out negative grams. Can you weigh out negative grams on the balance? No, you can't.
Well, I think I understand the problem. I think if you have it as x squared divided by 0.0125 minus x, it's undefined at 0.0125 because you'll get x squared over 0 when x is 0.0125.
Oh. All right. So it did that. Huh? Okay. So we know that we have to choose this one, this x value here. All right, and then what we're going to do is we're going to plug that back into our equation here. And so our amide concentration at equilibrium is going to be 0.0125 minus 0.0125, which gives us an equilibrium concentration of amide of 0 molar. And then the ammonia concentrations is going to be equal to 0.0125 molar. And our hydroxide ion concentration is equal to 0.0125 molar. And so the change was big. How big was the change? The change was we lost all of it. If we lose all of it, what do we say the change is? It's 100%. And so we had a 100% reaction. Or 100% hydrolysis. It's a hydrolysis reaction. So we say that strong bases hydrolyze water 100%. Correct? So that seems okay because we expect strong bases to hydrolyze water completely. Weak bases partially hydrolyze water. However, if that's the case, what are we doing with this 10 to the 20th? And so one of the common things we do in ice calculations is we double check our calculation. And so the way we double check our calculation is like this. We double check our calc. And we double check our calc by plugging the equilibrium concentrations back into the K expression. So K is equal to the ammonia concentration. Our ammonia concentration is 0.0125 times our hydroxide concentration, which is also 0.0125. So it's 0.0125 squared divided by our ammonia our amide concentration, which is 0. And so what does that give us? Undefined. This approaches what? Infinity. So K is, well, we're just going to say K is equal to infinity. So is that close? I mean, K should be 10 to the 20th. That's our value. And we're getting infinity. Is that close enough?
No.
No. Okay, let's calculate the percent error in our K values. So the percent error is going to be our experimental, that is, what we just calculated, infinity, minus the accepted value. The accepted value is 10 to the 20th, divided by the accepted value, 10 to the 20th, times 100%. And our percent error is going to be about infinite percent error. Would you say that's a pretty good calculation? No. That's not a very good calculation. So what went wrong? What went wrong there is your calculator. Your calculator is not designed to handle this many digits. It's going to screw it up. And obviously, whoever wrote the quadratic program there didn't write it to carry that many digits. There are probably fewer digits than your calculator, and so it screwed up the program there. It was exceeded its capacity. So what we're going to do is we're going to try something else. And what we want to do is we want to try to make the change as small as possible. And there is a way to make the change as small as possible. And so these are common tricks that we use to simplify the math. So tricks to simplify the math. And the first trick is that we want to reset the initial conditions if favorable. Let me do it like this here. Let's say I have a tank, water tank, and it's a weird shaped water tank. Let's say I want to put 50 gallons of water in here, but I'm going to put all 50 gallons on the left side, which I'll call the reactant side here. So the reactant side has 50 gallons of water, and on the product side, I'm going to have 0 gallons of water. Is the change going to be big or small? That is, right now all the water is here, and then I'm going to open the door here and let the water flow from left to right. Am I going to get a lot of water moving, or just a little? A lot of water. And so here we expect a big change. To be big, large change. So what I'm going to do here is I'm going to try resetting. So now what I'm going to do is I'm not going to add any water or remove any water, but all I'm going to do is I'm going to take all 50 gallons of water and put it on the right side. So now my product side has 50 gallons and the reactant side has 0 gallons. Now in this case, what do you expect for the change? The change should be a lot smaller, right? Change should be small. Okay, then we let it reach equilibrium. And it doesn't matter, as long as I don't add or remove water, it doesn't matter which direction I approach equilibrium. I'm going to end up at exactly the same equilibrium. And so as long as I don't add or remove, I just have 50 gallons, what's going to happen is it's going to reach some equilibrium, and the equilibrium is going to be the same for both. And so let's say the reactant side can only hold 1 gallon here. So let's say the reactant side, there's 1 gallon, and on the product side, we have 49 gallons. This is the product side. And so, because these reactions are reversible, it doesn't matter which direction we do. So what I can do is, if I have a reaction, I can push all the atoms to one side, or all the atoms to another side. You know, it depends on the limiting reagent. Sometimes I can't push all of them because there's not enough reactant. But what I want to do is, the strategy behind this is to make the change small. Why do I want to make the change small? The reason I want to make the change small is so that I can avoid round-off error. Let me give you an example of this here. Let's say the change were 99%. If the change were 99%, that's fine. That's 2 digits. That's 1 out of 100. So we had a change of 1 part out of 100, right? What if we had a change of 99.9%? A 99.9% change is 1 part out of 1,000. Or 99.99, that would be 1 part out of 10,000. What we need is a change that's 1 part out of 100 million trillion. A change that's like 1 part out of 100 million trillion is 1 out of 99.999999999. How many nines can your calculator handle? Yours can handle 12, mine can only handle 10. So my calculator can only handle a change that is 1 part out of, let's say, 10 billion, right? Then it's okay. But if you had something even smaller than that, you're going to run into trouble. And so the problem here is this. If you have any change bigger than the 99.99999, 10 digits, then it's going to round it to 100%. Well, 100% is not accurate. And so we do it this way. If the change is small, then we have one more thing we could try to simplify the math. So this will be number 2. I have one more of these tablets, but I can't find it. So I might have to buy a new one. Okay, if the change is small, is expected to be small, then try using the simplifying assumption to make the math easier. Simplifying assumption, I'm going to read SA. to make the math easier. This is number 2. All right, and so we're going to do both of these for this particular problem here. So the first one gave me an infinite percent error. It's too high. We're looking for a small percent error. So I'm going to reset this. This is heavily product favored, so I'm going to reset to the right. When I reset it to the right, I look at for the limiting reagent. I have amide and water. Which one's the limiting reagent, amide or water? Amide. I have plenty of water. I have so much water I don't worry about it. I have so much water that its concentration doesn't change and its activity doesn't really change. And so I reset it, and so what I do is I go minus y, and then the water I'll just ignore, plus y, plus y. And so the amide's the limiting reagent, and so what I'm going to do is I'm going to lose all of it, minus 0.0125. So what I'm going to do is I'm going to push all the atoms to the right side. This is going to be plus 0.0125, and this is going to be plus 0.0125. And so I'm going to get my new initial conditions. My new initial conditions is 0 molar amide, water is ignored, and then ammonia is going to be 0.0125 molar, and the hydroxide is 0.0125 molar. Okay, now the change is going to be in the opposite direction, is we got to add to the 0. So we're going to add to the 0 plus x molar. And over here, this is going to be minus x molar, minus x molar. So at equilibrium, I'm going to have x molar amide, 0.0125 minus x molar ammonia, and 0.0125 minus x molar hydroxide. And so we'll calculate, once we figure out what x is, we're going to calculate these concentrations. So I'll save a little bit of room underneath here to calculate it. All right, so let's figure out what x is. So we need to determine x here. This x is not the same x as the previous problem. And so the k value is 10 to the 20th, or approximately 10 to the 20th. This is going to equal the ammonia concentration, 0.0125 minus x, times the,
Go back up a little bit.
yeah. Times the hydroxide ion concentration, so this is going to be squared here. This is going to be divided by the amide concentration, which is just x. So actually the math isn't terrible. This is a quadratic equation. We can go ahead and solve it, but what I'm going to show you is this trick number 2. So that's trick number 1. Trick number 1 is we want x to be relatively small. And so this reaction is heavily favored in the product direction because of k. You know, k was about 10 to the 20th. And so that heavily favors the product. If it heavily favors the product, then we're going to lose very little product to form reactant. We don't need much reactant because it's 100. Essentially, this is just, it's more difficult because it's squared on top and to the first power on the bottom. But essentially, it's like 100 million trillion to 1 ratio. And so we're only going to lose like 1 part out of 100 million trillion, which is very small change, right? So for example, let's say you had a swimming pool full of water and somebody took a drop of water out of your swimming pool. If somebody took a drop of water out of your swimming pool, did the volume change? Yes, the volume changed. But did it change significantly? Are you going to worry about it? Maybe, maybe not. I mean, should you worry about it? One drop? Nah, I wouldn't worry about it. I wouldn't worry about it at all. Because the volume barely changed, one drop of water. And so this is how the simplifying assumption works. You don't worry about the change, basically. And so we're going to solve this in two methods here. We're going to solve this with the quadratic. And we're going to solve this using the simplifying assumption or simplifying assumption. So I'm just going to go ahead and use the simplifying assumption to do this. What the simplifying assumption is going to say is that the change is much, much smaller than the initial. So even though 0.0125 is a small number, we're going to say that x is even smaller. We're going to say that x is much smaller than 0.0125, so that there's barely any change. Okay, so we assume this. We assume that x is much smaller than 0.0125. Therefore, 0.0125 minus x is going to be about 0.0125. It barely changed. So if you have a swimming pool and you have a swimming pool minus one drop, well, the swimming pool minus one drop is just going to be about the swimming pool's worth of volume. So it doesn't change. Okay, now let's go ahead and solve this. Going ahead and solve this, we have k, which is about 10 to the 20th. This is going to equal 0.0125 minus x, quantity squared, divided by x. And then we apply the simplifying assumption. So when we apply the simplifying assumption, I'm going to write SA over this. And that's going to give us 0.0125 minus x is just 0.0125. Quantity squared. Now, what about this other x? Should I ignore this other x down on the bottom? I already ignored this x. Yeah, it's not a big deal. Just ignore it. Should I ignore this x? And the reason that I can't ignore this x, because let's say you're out in the desert and you're lost in the desert. It's already been 1 week that you've had no water. I don't know if you can live for 1 week. You'd probably die. Let's say it's been like 3 days since you had any water. I think you could survive. But how many days could you survive without any water?
Probably like 3 days.
Probably like 3 days. So let's say you're on your third day with no water. Is one drop of water significant or insignificant? I mean, to you, would it be? It's insignificant, yes, but is it significant?
No.
I mean, if somebody offered you one drop and you've already had no water for 3 days, would you take it or would you just say, that's not enough? I'd take it. I mean, one drop, come on, one drop of water out in the desert, that's a lot. So, in other words, if you had nothing and now you have something, something is significant compared to nothing, right? And so here we cannot ignore that x. That x is significant because we're comparing it to 0. I mean, they were looking for water on Mars for a long time, and if they found one drop of water on the Mars, they'd be jumping for joy because that would be a huge discovery, wouldn't it? But apparently now there's some big frozen crater of water on Mars. Did you hear about that? Mars is very hot, so how did the water stick to the surface there? And they're saying because of the weird thermal properties of this crater that the water didn't all boil away. So that's pretty impressive. But let's say you're on like an even hotter planet than Mars. What's a hotter planet than Mars? If you find a drop of water there, that would be a huge find, isn't that? So when we do this, x is significant compared to 0. So we leave the x there. But take a look at what happens to the math. Now the math is quite simple. So we'll just go ahead and solve for x. So x, I'm going to do 0.0125 squared. Actually, I'll just write it here. 0.0125 squared divided by 10 to the 20th. And x is going to be 0.0125 squared divided by 10 to the 20th. 1 times 10 to the 20th. My calculator. And I get 1.5625 times 10 to the minus 24. Am I allowed that many sig figs? No. You know, at the most in this particular problem, I'm allowed 1. I mean, 10 to the 20th has no sig figs. But I'll just make it 1 sig fig at least. But do I want to round this? I don't want to round it yet. I don't want to round it yet because I'm not done. You know, if you ever round, you round at the very end. Uh-huh.
Actually, 10 to the 20th has 0 sig figs. Doesn't have 1.
If you throw it in there. If I wrote it like this, if I wrote it 1 times 10 to the 20th, then that would have 1 sig fig. If I wrote it 1.0 times 10 to the 20th, that would be 2 sig figs. 1.00, 3 sig figs, right? Since there's no coefficient here, the coefficient contains the sig figs. The exponential term does not contain any sig figs. So based on the way I wrote it, it's kind of like no sig figs. But we're just going to, it's got to be 1. It's got to have at least 1. And so it should be really written 1 times 10 to the 20th. But what did they give us in the problem? In the problem, they didn't even give us that. When we go back to the problem, what they're saying is that the order of magnitude could be different. We can't be that precise. And so when they write it like this, what they're saying is that maybe it's 10 to the 20th, or maybe it's 10 to the 19th, or maybe it's 10 to the 21st. You know? So if I bring it down to 1 sig fig, like 1 times 10 to the 20th, that's really narrowing it down, because if I wrote 1 times 10 to the 20th, then what's the uncertainty there? The uncertainty is going to be between 0.5 and 1.5 times 10 to the 20th, which would be way too narrow. And so this is what I mean by 0 sig figs. It's not the sig figs that we're accustomed to. Uh-huh.
So you say that in order for us to use like these tools, like shifting it to the right,
Mm-hmm.
it has to be when the numbers are really big and or really small.
Yeah, the strategy goes like this. If the number is really big, K, shift it to the right, reset to the right. If the number is really small, reset it to the left.
And is there like I guess like about an amount in which we start doing that?
I try to do it for almost every calculation. I try to do it for almost every calculation because it works more effectively when we're talking like 1,000 and up. You know, then it works okay. But the closer we are, let's say between 100 and 1/100th, it may not work as good. But there's another strategy. The other strategy for resetting it is to reduce the number of binomials. Here I increased the number of binomials, but it was worth it. So we do little things so we can just simplify the math. If I look at my original calculation up here, there was only one binomial right here. After I reset it, then I end up with 2 binomials. 2 binomials is more work, the algebra. But there is a benefit, and the benefit is if the simplifying assumption works. Now the simplifying assumption works with larger, like k values of greater than 1,000 or less than 1/1,000, something like that. But regardless, I try for everything. I try for everything because it doesn't take that much time. If you look at this, I no longer have to use the quadratic equation solver in my calculator. I could just use the regular keys here, right? And so this was very quick. The calculation was very quick. X is equal to 1.5625 times 10 to the minus 24. Versus this. Let's go ahead and get this into quadratic form. And so I'm going to go ahead and solve this. Oh, but before I do that, I have to confirm the validity of my simplifying assumption. The simplifying assumption so SA is valid if the percent change is less than 5%. The smaller the percent change is, the better. The percent change in this case is, what was the change? So the change is x, 1x. The initial is 0.0125. So the percent change is the change over the initial times 100%. So percent change is the change calculated using SA over the initial times 100%. And so let's go ahead and do that. The change here is going to be x. X is 1.5625 times 10 to the minus 24. I think that was it. Let me verify that. 1.5625 times 10 to the minus 24. The initial is 0.0125 times 100%. And let's go ahead and calculate what the percent change is. So divided by 0.0125 times 100. And I get a percent change of 1.25 times 10 to the minus 20%. Is that less than 5%? Yeah. That is way less than 5%. The smaller the percent change, the better. Because as the percent change grows bigger, the simplifying assumption becomes increasingly an error. And so the larger the percent change, the more error we expect when we apply the simplifying assumption. And therefore, when I see a number like this, 10 to the minus 20 versus 10 to the 0, it's huge. It's orders of magnitude. And so this is very, very good. In other words, if it's very good, then SA is reliable. As we get closer and closer to 5%, then there's going to be a significant difference in doing the quadratic. In fact, the closer we get to 5%, or if we go over 5%, then we can't do it this way. We've got to use the quadratic formula. Otherwise, our answer is going to be in significant error. And so I think this is very good, but let's go ahead and solve this using the quadratic equation to compare the two and see how different the answers come out. And so over here, I'm going to go ahead and get this into quadratic form. That's going to be k is equal to 10 to the 20th, which is 0.0125 minus x squared divided by x. And so I'm going to go ahead and multiply both sides by x. So I'm going to get 1 times 10 to the 20th x over here on the left, and then let's go ahead and multiply this out. This is going to come out to x squared minus 0.0250x, and then what's 0.0125 squared? 0.0125 squared equals, this is going to be plus 0.000015625. 0.000015625. me erase these. This was talking about sig figs here. All right, so what I'm going to do is I'm going to subtract 1 times 10 to the minus 20th x. 1 times 10 to the positive 20x from both sides. So 10 to the 20th is what? 10 to the 20th would be 100 million trillion. So if I do 100 million trillion minus 0.0125, so let's say you had 100 million trillion dollars and you lost 2.5 cents. Is that significant? Punch it out in your calculator and tell me, can your calculator handle that calculation, or is it too much for your calculator to handle? It's too much for your calculator to handle. Your calculator can't handle it, and what is it going to give you as an answer? It's going to just say it's insignificant. So that's kind of like the simplifying assumption. We just used it here. I'm assuming that if I have 100 million trillion and I lost 2.5 cents out of 100 trillion million, I'm still going to have 100 trillion million dollars, right? And so that's what I do. Or you punch it in your calculator and you'll see, you'll get the same answer. And then this is going to be plus 0.000015625 is equal to 0. Now, I don't like to do the quadratic by hand. So this is why I mentioned to get the calculator. And so I'm going to try it here and see if my online version works this time. Point 0.0001562.5, as I recall. B was minus 100 million trillion. Let me just double check that. Yeah, minus 100 million trillion, and C was 0.0001562.5. Got it. Okay, that looks right, and then I'm going to calculate it. And let's see my answer here. My answer comes out that x, they gave me an x value of 100 million trillion. Or 0. Let's see if either of those answers make any sense. So I start off with 0 molar, and then I end up with 100 million trillion molar. And then I start off with 0.025, and I subtract 100 trillion million, and I get what? Does that answer make any sense? No. The other answer that we get is x is 0.
It's so small it might as well be 0 in all regards.
They're saying it's so small it might as well be 0, but if I'm on a planet that has no water and there's a drop of water, I'm going to be very excited, because that drop of water could mean that there's even more water, right? But anyway, if I put in x is equal to 0, what's my percent error going to be? Infinite percent error. So the quadratic solver online sucks. Be careful with these. This probably only carries like 5 digits or whole numbers. You know, maybe they'll only do whole numbers because there are better quadratic solvers out there. I've used them. I've used quadratic solvers that work pretty well, but this one is bad. The calculator soup and the one I tried before. The quadratic formula, oh, this is calculator soup. And well, the other one I tried was calculator.net. That one failed too. But you got it on your calculator? So the TI pulled through. And so what did you get using the TI?
1.56 times 10 to
Give me more digits.
1.5625.
The reason I like to carry a lot of digits is because I can tell if the error is due to round off, or if the error is due to a calculation error. If I round everything off, then I can't tell. You know, I'm off. My percent error is high because of rounding, or is my percent error high because I made a mistake in my calculation? What happened to my... what was it? 1.5625 times 10 to the minus 24? Okay. Now let's compare. We got this without making any assumptions, and we just went ahead and solved the quadratic equation. No assumptions. We got this answer using the simplifying assumption. What's wrong with this thing here? So by using the simplifying assumption, we got 1.5625 times 10 to the minus 24. By using the quadratic formula, we got 1.5625 times 10 to the minus 24. Any difference? No difference. No difference is what you expect when the percent change is small like this. If you have an exceedingly small percent change, then it's very good. It's not even worth doing the quadratic. You know, if you got something like this, you're going to get the same answer using the quadratic anyway. So you might as well use the simplifying assumption. It takes a lot less time, you know, than getting this into quadratic form. And so here's a case where we use the two tricks. And now we're going to double check. So we got an x value of 1.5625 times 10 to the minus 24. So that means this here. Let's do this. X is 1 point, actually, let me narrow this down. That's not going to work. X is equal to 1.5625 times 10 to the minus 24 molar. And then I go over here and I do 0.0125 minus x. 0.0125 minus x. Is x very big? No. And so this is going to come out to 0.0125 molar. And this, you can punch out in your calculator. Your calculator can't handle this calculation. 0.0125 molar. All right, now let's double check. We're going to double check our calc, and that is K is equal to 0.0125 times 0.0125. And that's going to give us 0.0125 squared. This is the ammonia times the hydroxide. Divided by 1.5625 times 10 to the minus 24. So can you punch this in your calculator and tell me what you get? All right, one, and your calculator carries 10 digits, so I'm going to just add them in here. 1.0000, that's 3, 6, 9, 10, times 10 to the 20th. Okay, now let's calculate our percent error. What is our percent error? Our percent error is going to be, it's going to be our calculated value, 1 times 10 to the 20th, minus the accepted value, 1 times 10 to the 20th, divided by the accepted value, 1 times 10 to the 20th, or 10 to the 20th, times 100%, and our percent error comes out to 0% error. So what would you rather have, a 0% error or an infinite percent error? Obviously, a 0% error. And so we have to watch out for our calculators and also these online calculators. You know, we can easily overwhelm them. This is 0% error, which is good. And so these concentrations look good here, and these would be the equilibrium concentrations that we expect. Now, what bases do is bases produce hydroxide. And what it means is that it makes the solution more and more basic. The more hydroxide, the more basic. So weak bases partially hydrolyze water and make a little bit of hydroxide. Strong bases completely hydrolyze water. Or actually, this is not complete. What is the percent reaction here? Let's try to figure out what is the percent reaction here.
Basically 100.
Basically 100, but I want to know. Okay, so the percent reaction is this. I usually calculate the percent reaction like this. The percent reaction is equal to 100% minus the percent remaining. So the percent reaction is the percent lost, and the percent remaining is the percent that is left over. So this is going to be 100%, and the percent remaining is equal to the final amount, that is the equilibrium, over the initial amount times 100%. Okay, so the final amount is 1.5625 times 10 to the minus 24. So this is going to be 100% minus, okay, the final amount is 1.5625 times 10 to the minus 24. What was the initial amount? Now this is tricky because we have two initial amounts. We have the initial amount before resetting and the initial amount after resetting. Which initial amount should we use? Before. We have to use the initial amount, the original amount that was in there. And so we only have 1.5625 times 10 to the minus 24 molar of the original left over. And the original was 0.0125 molar. And then that's times 100%. And so we're going to get 100% minus, okay, so I'm going to do this way. I'm going to do 1.5625 times 10 to the minus 24 divided by 0.0125 times 100. And I get 1.25 times 10 to the minus 20. Okay, and then I'm going to change the sign on that and add it to 100. Can your calculator handle it? When you punch this in your calculator, what do you get? You got 100%. But I don't want 100% because 100% is called round-off error. And that's because of failure of your calculator. And so what I'm going to do is I'm going to go ahead and calculate it down here. That's 100%. This is not working. There we go. Come on. My word is going to crash soon. All right, it crashed. My word crashed. I'm going to switch to Excel. And do it here. So we have 100% minus, what was it? 1.25 times 10 to the minus 20. So 1.25 times 10 to the minus 20, I'm going to convert from scientific notation into decimal form. So I need 19 zeros. 1, 2, after the decimal. So decimal place, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then a 1, 2, 5. And so what I'm going to do is I'm going to 19 zeros past the 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I didn't line it properly. And then 3 more zeros here. And so this is going to give me 99 point, I'm going to put 19 nines. 1, 2, 3, 4, 5 after the decimal. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then it's going to be 8, 7, 5. So I'm going to have 99.9999999999999999875% reaction. Here. Okay, so it's about 100% reaction, but not exactly 100% reaction, correct? It's very close. Is it very close? I don't know. How close is this? And so what we're going to do is we're going to do this now. You know, I know there's going to be a tiny bit remaining. And how much was remaining? How much was remaining was this. There was 1.5625 times 10 to the minus 24 molar amide unreacted. And so if I have a liter, so how many amide ions in a liter? Can you calculate that for me? How many amide ions would you find in 1 liter of this solution? Let me pause this here. So this, we just use dimensional analysis. So if I have 1 liter, I'm going to have 1.5625 times 10 to the minus 24 moles. And then I'm just going to use Avogadro's number for that. So I'll just do 1.5625 times 10 to the minus 24 moles times Avogadro's number, 6.022 times 10 to the 23rd. And that gives me 0.94. 0.94 ion per liter. And so I'd need more than a liter just to find 1 amide ion. Is that much? No. And so this is why we say that strong bases hydrolyze completely. You know, it's awfully close to complete, right? Just 1 ion left over. 1 ion left over in a liter, or less than 1 ion. This is less than 1, not even 1 ion. In 2 liters, we'd have a little more than 1 ion. So, but not quite 2 ions. All right, any questions on this? No. So what we're going to do is we're going to take a break. Can you check out the equipment for today's lab from the stock room? Yeah. So we'll take like a 15-minute break, and then after that, we'll start talking about today's lab.